Okay, g'day and welcome. My name is Brendan, and at Illumos Day today I'm giving a talk on DTracing the Cloud, which will include interesting visualizations that are DTrace backed. I do performance analysis of the cloud. I work at Joyent. I use the right tool for the job. That can be traditional tools, such as Solaris Performance and Tools, which I co-authored, and which I'm very familiar with, but I'll use DTrace when needed. DTrace itself is a magician that conjures up rainbows, ponies, and unicorns, and does it safely in production. That's a great graphic we had for the DTrace convention, or the version with fewer ponies. It is a performance troubleshooting and analysis tool, and it instruments all software, kernel, and user land. I imagine a lot of people in the room know this very well by now. We love asking this question. I don't get tired of it, but hands up if you've used DTrace. Hooray! This is fantastic. We're getting to almost 100%. So that's great. I was at the Surge conference on Friday, and we had a very large number of people who used DTrace there as well. So I don't need to. In fact, it's great because I can do fewer of these intros and do more content. So we know what DTrace is. Illumos, Joyent SmartMachine, uses and contributes to the Illumos kernel. Illumos is the most DTrace featured kernel, and it's due in part to us having people from two of the fathers from DTrace, including father and son. Father and son, as the picture might indicate. So actually, this picture's great. On the left, you've got Garrett, and you heard from Garrett this morning. Garrett gave the keynote. You've got Matt Ahrens. You'll hear Matt talk about ZFS tomorrow. Brian Cantrell and Adam Leventhal on the right. Adam's just over there. And Adam's giving a talk later today about Illumos features. So what a great picture of the happy Illumos family. At least some of the people in the family. What I'm going to talk about is some theory about cloud types and DTrace visibility, and then some reality of how this actually works. We have a great perspective at Joyent since we do this for a living. We use DTrace on the cloud, and we get to find out what does work and what doesn't work. For us, this isn't a theoretical exercise. The reality is where I get to describe how it actually works using DTrace on many systems. I'll go through some tools that I wrote that we tend to use for DTracing the cloud, and then I'll go through some case studies. So, theory. We deploy two types of virtualization on SmartOS and Illumos. We use hardware virtualization, KVM, and OS-based virtualization, zones. And some of this might be very familiar to you, just background theory. Both types of virtualizations can coexist on one server, which we call a compute node. Here I've got the host kernel is SmartOS, and we have two guests, which are using KVM for hardware virtualization. They have their own kernels, and we have a SmartOS, what Joyent calls a smart machine, but it's using the zones technology, and that's another cloud tenant. KVM, we use it at Joyent as our hardware virtualization. That's used for Linux and Windows guests and for legacy apps. We try as much as possible to get people to use SmartOS smart machines. They're preferred over Linux because you get the bare metal performance. You don't have to go through any sort of virtualization translation layers. You only have one kernel managing the devices, no emulation. There's less memory overheads, and so in terms of cloud computing, it becomes very important the density that you can put systems on each compute node, and that's very good for the OS-based virtualizations. Better visibility, which I'll talk about in this presentation for debugging. If you're familiar with the zones terminology, the global zone from zones is what we use as the host, although not quite the same thing, but almost the same thing. The non-global zone is what we have for the guests, the SmartOS tenants. DTrace itself can be used for performance analysis, user and kernel level, troubleshooting. Specifically for the cloud, the performance effects of multi-tenancy, the effectiveness and troubleshooting of performance isolation. So one of the biggest performance issues for people running clouds is I have other tenants who are doing particular workloads. they're using CPU, they're performing disk I/O, they're performing network I/O. We have various ways to isolate the performance to those tenants. How effective is that? If I'm logged into my guest and I experience a performance issue, is it because another neighboring tenant is performing a backup or a benchmark? And so answering those questions becomes very important to us. We especially like DTrace and the transparency it provides. There are other cloud providers where you're kind of left in the dark and you don't have the tools to answer this. And so noisy neighbors becomes a real problem. But we like to arm our customers and our operators so that we can identify quickly. Now there are 4 contexts for DTracing in the cloud that we do. We've got the KVM host, the KVM guest. Those are the Linux and Windows SmartMachines, the Linux and Windows KVM guests. Then the zones host and the zones guest, and the guest is the smart machine. A frequently asked question is, what can DTrace see in each context? So for hardware virtualization, DTrace, and I've drawn DTrace visibility as the yellow box, DTrace can see what the host kernel is doing and the virtual device drivers that are plugged into the host kernel. You can't really see into the guest kernel. You can see when the guests perform I/O, and you can, that might give you some information about network I/O and especially disk I/O, but you have a limited amount of observability. When these things actually run inside KVM, they're key move processes, and if you run top or PRStat, you can actually see a process ID that's running, and it's hard to see inside it because it's running its own kernel. And to list them out, the host can see so if I'm the cloud operator and I'm logged into the host, I can see the entire kernel and the applications it's running. I can see the guest disk I/O at the block interface level. I can see guest network I/O packets. I can see the guest CPU MMU context register. It's a trick Robert Mustaki came up with. So you can identify if threads are switching within the guest, because based on the emulation of its MMU. But the host can't see a lot of things. You can't see inside the guest kernel. You can't see the guest applications. You can't see disk and network from the guest context, which is really useful. Why am I performing disk I/O? Why am I performing network I/O? What information from the TCP stack is happening, such as have I got drops from the kernel? How's my TCP backlog? All these sort of questions we take for granted you can't see from the host when you're running hardware virtualization. Unless you've configured, unless the guest happens to have DTrace, the guest could be running DTrace, depending on the operating system, and you'd have to SSH onto the host to be able to run it, or use some other API. If the tenant guest did have DTrace, you'd be able to see yourself. But you couldn't actually see the bare metal, what you're actually running on. The device is managed by the host kernel. So the guest could see the guest kernel, the apps, provided DTrace is available, but you can't see everything else. Now compare this to OS virtualization. This is one of the reasons we get excited about OS virtualization. As the cloud operator on the host, I can see everything. I can see all of the cloud tenants, I can see the host kernel, I can see the applications that they're running, and I can see the interactions between them. And so I can confirm if one tenant is doing a backup, and I know they're doing a backup because I can see the process, or if they're doing a database dump, are they interfering with the disk I/O of another tenant? And I can go into the kernel inside ZFS and measure the effect, the multi-tenancy effect. So host can see everything, which means the operators get to see, can trivially see the entire cloud. Direct visibility from the host to all tenant processes. So you may not know much about how zones work, but from the host, I can see the process address space for all of the tenants that are on that machine or that compute node. The background of this picture is one of our data centers or an availability zone where I've taken this isn't using DTrace, it's just using PS. I've taken a process listing of every machine and every node in the cloud and then graphed them. And so each of those blobs is actually a tenant in the cloud. And there's thousands and thousands of tenants. I forget which, this is the US EV3, where's Ryan? Where's EV3 based?
Emeryville.
Emeryville. So this is the Emeryville data center of Joyent, of course. Zooming in, so that's what one host looks like, which has 10 guests. I've got a website if you're interested in that type of visualization. Each of the circles or ovals is a process, and it has mapped the parent-child relationship. I've colored them just so that I could see web-based processes like Apache in red, Perl or PHP in green, MySQL is in purple. That's just one machine. So you log into the host on one machine, you get to see all of that without having to SSH onto each client or do anything fancy. And if I am a cloud operator and I'm building up an observability infrastructure, it means I can reduce the overhead to monitor the cloud by a factor of 10, or whatever the guest to host ratio is. As a tenant on the OS virtualization, you get to see yourself. I've drawn a dashed line because you don't get to see everything. You get to see things that you're supposed to be able to see. You can definitely see all your applications and what you're doing to the system call interface. You get to see some kernel visibility as well. So your apps host kernel in guest context so that there's no sharing of information between tenants. You can't arbitrarily view the kernel so that you could see someone else's information. That's the scopes of DTracing the cloud. Just very quickly is the form of theory. Now for the actual visibility of DTrace, I just quickly drew up this colored diagram of the entire operating system stack. You sometimes hear people say that their observability tool has entire stack visibility. People use that term differently. Sometimes they mean it is the application stack. And so you're looking at MySQL, Apache, and PHP. Often when I say it, I mean the entire software stack, the operating system as well as all the applications. And DTrace allows you to examine everything except for the device itself, except for the firmware on the device and the actual electronics of the device. But I can see everything else that the kernel is doing. That's the theory. So we have this fantastic visibility. And if people are running in OS virtualizations, which is what we at Joyent encourage, the operators see everything, the tenants can see a lot of things. On hardware virtualization, is not as rosy. The reality of using DTrace in zones, which is what we've got for OS virtualization, DTrace in zones were developed in parallel for Solaris 10 and then integrated. DTrace functionality for the global zone was added first. And this is the host context. And so that allows operators to use DTrace and to inspect all tenants. And so you've got things like zone names so that you can see you can correlate the context from activity to the actual zone. DTrace functionality for the non-global zone was harder, and some capabilities have been added later. So you have 3 providers: the syscall provider, the PID provider, and profile provider. And the idea is you get to see yourself, you can't see other tenants, you can't see into the kernel. You basically get to see guest context. Here's a nice picture from last year. This is Solaris, #1 enterprise OS built for clouds at Oracle Open World. I don't know if this bus is still driving around this year. I hope it is. It's a great picture. This kind of implies that Solaris on clouds is great, and we definitely believe so. We have the same heritage with the Illumos kernel. Our experiences in practice did get a bit rough. As I just mentioned, the non-global zone capabilities were added later because it was more difficult. And so we've found that there were many issues doing non-global zone DTrace observability in the cloud that we've been fixing up. So for example, you can't read FDS to translate file descriptors. And that makes using the syscall provider more difficult. There's a lot of scripts in the DTrace book and that I've written that use the FDS array. You can't read car psinfo or car LWPSinfo. That breaks many scripts. Sadly, it breaks one of the top one-liners of DTrace. So syscall exec star return, trace car psinfo, PRPS that shouldn't happen. It's really sad when one of the top one-liners doesn't work. And we're missing the proc provider. It breaks that common one-liner. Proc exec success. I can't even switch to exec name. We're missing vminfo, sysinfo, and shared providers as well. You can't read the CPU built-in. And profile probes behave oddly is another one that we encountered. That was particularly frustrating in that I have a lot of scripts that will sample activity or trace activity and will give you the per second averages, give you the per second report. Those scripts just generally don't work inside non-global zones because of the way the profile tick probe wasn't firing properly unless that tenant happened to be on CPU. So these were bugs that needed to be fixed, and Brian Cantrell has done a lot of work. They've been fixed for SmartOS and Illumos. And now, from a SmartOS zone, you can run this, DTrace-n proc exec success, aggregate on CarPSinfo PSArgs, and it works, which is fantastic. This absolutely did not work. Multiple things did not work before. And I've got the profile tick 5 seconds, so it runs for 5 seconds and then exits. There are 3 reasons why this doesn't work on prior Solaris. So things that needed to be fixed. The proc provider, the CarPSinfo, and the profile tick provider all needed to be fixed. And it's a trivial DTrace one-liner. This should work. We were reminded of it because we had some customers move to the cloud because they wanted to use DTrace on their apps. And they opened up my DTrace book, I've got a copy of it here. They opened up my DTrace book and said, it doesn't work. The first examples don't work inside the cloud. And we had to go and fix a bunch of these things so that they could enjoy DTrace. That's looking at some of the issues that we fixed, but I don't want to paint too bad a picture about DTrace. DTrace has been fantastic in the cloud, and we've fixed them as well. And we've solved numerous issues. A lot of these issues, unfortunately, are on the internal bug database. So I did a blog post recently where I did a wrap-up of 10 example issues. This is my life as doing systems performance analysis on the cloud, and 9 out of 10 of these issues were solved using DTrace. And the improvements vary. Often we're using DTrace. Sometimes it's about getting a broad 2x win or a broad 8x win. Often it's about finding outliers and eliminating them. And so that's why some of these say up to 380x and up to 2800x, because there were occasional events that were very, very slow and we fixed them. So DTrace wins. It's not surprising given DTrace's visibility. And I had this diagram earlier. It's one thing to say, yes, DTrace can do this. It's another thing to say, actually, if you read the DTrace book, I have examples for each of these areas. So like, you can actually browse this and see it's actually real. You can run the scripts. You can actually see all of this in detail. One of my goals of the DTrace book was to make sure I gave you at least a starting point for everything, so that you could take those scripts and then build upon them and customize them. And there are many more scripts in the DTrace book. I just quickly drew that diagram of there's at least this many for those areas. So that's some of the theory. So DTrace, different contexts, really good for the operating system virtualization. And we did have to fix some bugs for the non-global zone, but it's now proven it's been very valuable. To give you an idea of the sort of tools that we're using, so Ad-hoc, so there's 2 ways we can do this. There are Ad-hoc tools that myself and the operators use for the cloud, and so do customers. We write them as needed, and then there are solutions that are built upon DTrace. So for Ad-hoc, these are things that you execute individually on hosts, or with Ad-hoc scripting, you execute across all hosts on the cloud. So I might have just some simple shell script that goes and runs something on every single compute node or every single server on the cloud, and then gives me the output. I've got some examples to give you an idea of the sort of things that we do use on the cloud. DTrace Cloud Tools, I had this directory on my laptop for a long time, and I finally put it on GitHub so that people can see the sort of scripts. There's about 70 scripts in there. Previously, I wrote the DTrace toolkit, which I need to update. the DTrace toolkit came first, then the book came second, and I wrote an extra couple of hundred scripts for the book. And now I've written many more scripts for the cloud specifically. And so I've been putting them available there. There's scripts to look inside ZFS, and I've got a talk tomorrow where I go through some of these. Scripts to look inside MySQL that customers can run. Scripts to look at network I/O, so TCP, various TCP events like looking at accepts, looking at the tunables, whether they need to be tuned or not, for the TCP conrec maxq, TCP listen drops, TCP retransmits, TCP time wait interval, all sorts of, each time there is an issue, I kind of try and write the canonical small script that you can use for differential diagnosis. Do I need to tune this kernel tunable? Now, a lot of people use the experimental approach where you just take a swing at it and see if it works. It can be very helpful to have the 5-line DTrace script that gives you the data. And so a lot of these scripts are based on that approach. Just as an example, a very common thing we get in the cloud is TCP listen drops. And for cloud computing, customers want to scale. I want to be the next massive Facebook or Twitter. And for some of them, they're lucky enough, and we see this at Joyent, they're lucky enough to start getting the huge amounts of traffic. One of the first things to fall over is your application can't keep up with the rate of inbound connections. And what happens is TCP has a backlog in the kernel. You may know this very well, Networking 101. TCP has a backlog in the kernel, and when the SYN arrival rate is too fast, the backlog will hit its max, and the kernel will start dropping packets. These are SYNs the kernel's dropping. And it's if you're using Wireshark or you're looking at the network interface, you kind of have to figure it out based on retransmits. It's much, much easier to do this from the kernel itself. In fact, this is one thing Dan and I were really excited about in networking, to add drop probes inside the kernel for DTrace, so that we funneled all kernel code paths to one dropper that we can then detrace to make these mysterious network drops much, much easier to diagnose. And so here's a script I wrote, which I don't actually use the IP drop probes, but this was what we needed at the time, and I actually run this a few times a month when a customer thinks they've got this type of issue, and I can just immediately say, yes, the kernel is dropping your packets, right, because you've exhausted the backlog.
The other reason it'll drop is if you're under DDoS.
Yes.
Can you tell the difference by drop rates or incomings or whatever? Have you gone down that rabbit hole?
I haven't gone down that rabbit hole. So Dan says it could drop because of DDoS. I haven't gone down that rabbit hole, but you would see, actually no, I have, no, there was twice. And we knew it because this was thousands of events and the IP addresses were random. And it's like, what? Like, why are these like random people connecting to us? And of course the application, and the problem is the application's not just dropping the random DDoS, it's dropping your real customers, which is the whole point.
You can't tell the difference between a CNN moment and a DDoS.
Right. You can't tell, actually, that's the thing, you can't tell the difference between, it's hard to tell the difference between random DDoS and the big scalability event, the CNN event that you've been hoping for. And so, using a tool like this can help you as the customer quickly identify, yes, this is not a DDoS, this is real. I need to like immediately go and pull out my credit card and buy more nodes and scale up my cloud, which is why a lot of us are in the cloud business. And as the customer, you don't want to be doing that when it's a DDoS. It's like, those DDoS guys, they just cost me $10,000 because I bought all this extra hosting I didn't need. So you could definitely use tools like this, or ask the operator, because this actually needs kernel access. And the operator can help you identify whether it is DDoS or whether it is a CNN event. So I'm glad you brought that up. For reference, the internals of that script look like this. I am going into the kernel, FPT, TCP input listener, and then tracing MIB, TCP listen drop. Not a terribly long DTrace script, a little brittle because it is tracing internals of the kernel. And since it is tracing kernel internals, cloud customers can't run this particular one. This is for operators only. And you'll see this is one of those themes in practice, is there is a subset of scripts that the customers can run because they have permission, and then everything else the operator can run on their behalf often. Just as a different way to express that, this shows the TCP backlog length. And I'm printing the TCP backlog length as a distribution plot And it answers the question of, how close am I to dropping? I hear about this TSP backlog in the kernel. What does it look like? Wow, I can actually see it. This is the first time you can see the TSP backlog. That's what it looks like. Most of the time it's 0, and I'm counting it each time a SYN arrives. Once I get down to the 128 range, we drop. And there were 34 drops and 34 listen drops. On the left, the CPID is the process ID, and on the right is max Q, which is the current in effect setting. So if you're there setting system tunables, the application can override the backlog length, which makes it really frustrating when you're trying to tune it and your tuning is not taking effect. So this is one way to be sure. Another ad hoc tool is flame graphs, and this has been very popular. I've been using it for tracing, for profiling CPU usage, and it's also on GitHub. It allows you to quickly identify why your CPUs are hot and what code paths need attention. And so and we found that this is just a very popular ad hoc tool that customers are running, especially in Node.js, because we've added UStack support for that. So that was some ad hoc tools. Now for some products. Well, we've developed something called Cloud Analytics, and Cloud Analytics shows the you can have arbitrary instrumentations, but they are defined, arbitrary filters and predicates. For example, this one here is showing the system call latency decomposed by latency and system call. This is across the entire cloud, and this graph is pretty crazy. Unfortunately, I still can't explain it in detail. It's fairly new. It is showing, I've selected the read system calls, and it's showing that we don't have what you might guess as a single band of latency rise and fall, but there's different modes and there's patterns that are happening. And this kind of explains why we're doing latency as a heat map, which DTrace is very good at dragging out, because DTrace can give it to us in arbitrary detail. And it allows you to identify that the higher it is in the heat map, the higher the latency, and the lower it is, the lower the latency. This is done as a heat map instead of a scatter plot, because that's one of the things we found. To be practical at scale, you can't have a scatter plot of latency events or whatever events, because on a single server, I might be doing 100,000 syscalls a second. Across an entire cloud, I can be doing many millions of syscalls a second. And so in real time, you can't gather that data to 1 second granularity and plot it. But with a heat map, you can quantize the data down into buckets. So Cloud Analytics, this is something that Joyent created, and I've included it as an example of a cloud monitoring product that uses DTrace. This is for operators and cloud customers. It allows you to observe the entire cloud in real time, and it is DTrace backed. It's latency focused, so you get to see those really cool heat maps. The instrumentation is DTrace and Kstats. The front end is browser JavaScript, and the back end is Node.js and C. And to give you an idea of the sort of technical challenges involved for this, creating an instrumentation. So what we've got is a configuration service. We'll use a AMQP protocol to talk to each compute node, which is the servers running on the cloud tenants. And they have their own instrumenters running in the host or the global zone, and the instrumenter will instrument all of the tenants. Data is aggregated from the cloud at 1 Hertz. So every second, the instrumenters will send the data to the aggregators. And it's drawn this way because there are multiple instances of aggregators, because we need to actually scale the cloud analytics architecture to match the cloud, because there can be so much data that we need to gather together and process to generate these heat maps in real time. Visualizing the data is done a couple of different ways. Raw data requests for line graphs can be sent because there are only a small number of values. Heat map requests, we actually do server-side pings because it's too much data to send otherwise to the client. Actually, rendering it as a ping and sending the ping is a pretty efficient data protocol for sending that much data, rather than having some JavaScript library on the browser render the heat map. So one of the key design goals, apart from being able to watch the entire cloud in real time and to do things like look at latency from different levels, say MySQL, at the syscall interface, at the VFS interface, at the disk interface, we also came up with this notion of four dimensions for the heat map. Heat maps actually are a three-dimensional visual tool, and so you can see the depth is the third dimension. We obviously have two spatial dimensions. We use hue as a fourth to represent the fourth dimension because it's there in the data. And the most common breakdown we have, which is absolutely essential, is selecting the individual compute nodes or the individual hosts. And so we can bring up a heat map of the entire cloud and say, oh, it looks like there's a disk that's misbehaving, click on it, and then go straight to the host, and then from the host go straight to the cloud tenant and identify it that way. It was a technical problem, and because it inflates the amount of data you have to collect in order to have that extra dimension. But it's something we use all the time, and really accelerates how quickly you can go from an unusual latency event to analyzing, finding out the actual location. So that's some of the tools. I'll finish with some case studies so that we get to see some uses of DTrace on the cloud. Slow disks is the first one, and this is one of the first ones I worked on after joining Joyent and working on the Joyent public cloud. And it's also a very common one, it keeps coming up. A customer complains of poor MySQL performance, and they've noticed the disks are busy via IOStat-based monitoring software. And they've blamed noisy neighbors. It must be noisy neighbors. It's a sort of thing in performance. People tend to blame the thing that they can't see, which I guess makes some degree of sense. If you can't see it, that could be the reason for it. And obviously you've searched the areas that you can see. Multi-tenants and performance isolation are common cloud issues. And so people do come to Joyent from other cloud providers, and it's one of the first things they go for is, do we have disk I/O from noisy neighbors impacting our performance? And so this is, of course, is something pretty trivial for DTrace, just to go and answer, do you have noisy neighbors or not? I've drawn a diagram of just the Unix architecture, Unix 101. So processors talk to file systems and disks via the VFS layer, which Sun added in the 80s. You've got multiple file system types, block device interface to actually represent the disks, and then we talk to disks. The problem is IOStat works at the block device layer. And the block device layer is often asynchronous to what the process is doing. So you've got write buffering. My application writes to the file system cache and DRAM, and that gets synced out later to disk. ZFS in particular has transaction group flushes for asynchronous writes. Read ahead. If you're doing reads, streaming reads, the disk is going to be busy prefetching or reading ahead data into DRAM before the application needs it. And again, what you're looking at in IOStat isn't necessarily the same pain that the application is suffering, because it's at a different context. And of course, it's not just IOStat. There are a lot of observability tools built upon IOStat, and so these suffer the same issues. And so I frequently see customers looking at line graphs, which I know are originating from IOStat or KStat, the kernel statistics that Ben mentioned earlier, and you're only looking at one level. If you actually want to express the pain and then really get a grip on the effects of multi-tenancy, you need to go up to the VFS level or the process itself to look at the synchronous latency, the time you are actually blocked. So by measuring it from the synchronous context, we can confirm or rule out the file system or disk origin latency, such as expressing file system latency during a MySQL query. That would be ideal. This particular case study was for MySQL, and if I can express the time you were blocked on the file system as a ratio of the time you spent in MySQL, you would immediately quantify the issue, and you can also calculate speed up. If 90% of my time was blocked in the file system and I eliminated that, I could go 10 times faster, would be my theoretical max. So this sort of expression is ideal. Ideally, we would also get it from within the smart machine so that the customers could run it themselves. There are two ways to do that, using the PID provider to trace MySQL internals, and the syscall provider to look at the file descriptor to make sure that it, say, reads and writes, or P reads, P writes, that they were talking to file system files. So there's the tool that I wrote for the customer, and it's doing MySQL, file system latency, and it's showing the latency's distribution plots, and we can immediately see the distribution of latency. In fact, for the right one, you can see there's a very large group of DRAM cache hits. The left-hand column is the time in nanoseconds, and near the bottom you've got disk I/O in the 4 to 16 millisecond range, which makes a lot of sense. That's great for identifying outliers. So if you've got a case where my query is slow because I have these occasional 500 millisecond disk I/O, which I know sounds insane, but stranger things have happened on the cloud, this would identify it because you'd see the outlier right at the bottom. That script actually looks like this. It's only about 30 lines of DTrace, and thank you, MySQL. It was so easy because MySQL has OS file read, OS file write, myread, and mywrite as API functions for accessing the file system. So it actually made it a very trivial script to write. And a lot of you have said you've used DTrace. You'll see that this is actually a trivial script. It's measuring a timestamp when we enter the file system operations, and does the delta when we complete, and then does those nice distribution plots. Now, if you were on a different database and it didn't have these nice functions, you could go to the syscall provider and look at, say, read and write syscalls. The first argument is the file descriptor. That's why you need FDS, because on SmartOS, a lot of reads and writes could actually be socket I/O or pipe I/O or some other type of I/O. So that's one of the reasons we really needed FDS to be in the cloud. So going for the slam dunk, this does MySQL PDFS latency slow log, and I had customers run this 24/7, and it's only recording queries that were slower than 100 milliseconds. It gives you the query time and the time spent in the file system. And so from that you can calculate the proportion of latency that was due to the file system and the potential speed up. So this is the dream tool. And most of the time the customer found it was not in the file system, it was actually in MySQL on the CPU. For the cloud operator, I actually use ZFS slower.d, and I trace it from VFS, simply because I can run this across all applications and I'm not just tied to MySQL. So that's tracing I/O slower than 10 milliseconds. Again, this one was stupidly easy to do because we have a nice VFS mapping. And so I've got ZFS read and write. We calculate the timestamp and then do the delta. But as an operator, I can go anywhere through the stack as needed. So I can go through the different layers. I really feel like I've only done a fraction of ZFS detracing that is possible. There's a lot more that we can do as needed. Generally, I create the tools as we're working on issues to solve them. In cloud analytics, now this is for either the operator or the customer, we allow you to look at the full latency distribution, including outliers, as a heat map. And so this is actually pretty good at identifying the outliers. That's looking at the entire cloud data center and all disk I/O across the entire cloud. And so I bring this up from time to time, and I can just go click on the high spots and say, okay, we've got some bad disks over here. Sadly, sometimes the disk manufacturers, the disks don't give you error counts, and so the operating system doesn't know that it's hit an error. And so, and the disks exhibit very bad performance before they actually die. And so it's like an early warning that these disks are going to die. So to wrap that one up, the customer problem wasn't actually in the disks or the file system 99% of the time. It was the CPU usage during table joins, and we made it. The customer had spun their wheels on this for many months because they weren't using DTrace and they weren't able to identify it, and they assumed it was noisy neighbors, and it wasn't. It is some of the time, and it's really useful to have the tools to identify that, and I put some of the reasons there. Now, the last case study I had was Kernel schedule. I'll go through this quickly. This is an example of the customer had latency outliers. There was no smoking gun, no slow I/O or locks. There was some random dispatcher queue latency. So I've got the latency, CPU latency column of PRstat minus MLC. Now that's measuring the time we spend on the run queues. So this is Unix 101, you may know this very well. After the threads that are ready to run per CPU, and the time they spend on that run queue is the CPU dispatcher queue latency. There is, if that queue gets too long and threads are stuck there for a long time, there's this notion of priority promotion or CPU starvation. So if a thread has been queued in the ready to run state for too long, it will get promoted higher up in the queue to give it a better chance to run. Now, one thing we discovered, and I performed an experiment of 2 hot CPU threads, that this is doing a sub-second offset heat map of their runtime. And so it's doing, each on the y-axis is the offset within a second, and it's painting it like a TV raster. And what it shows is sometimes the threads would go on. Now, it should look like a checkerboard because there are 2 threads competing for the CPU. But sometimes the thread would go on CPU and stay there for a long time. And that really shouldn't have happened. And with some more analysis, the worst case showed that 4 threads in 1 CPU, you can have 44-second dispatcher queue latency, which is horrific. The CPU starvation should have kicked in by then and prevented it. It was a scheduler class bug, and Jerry Jelnick fixed that, and he'll be giving a talk later. It was analyzed using more DTrace. Under too high a CPU load, your runtime can be fixed by these. Your runtime can be bound by these sort of scheduler effects. And so we were able to go into the kernel scheduler and identify it. This is a nice example because things like this happen. People tend to think that the operating system is a solved problem, but with the cloud workloads, people are running crazy new things all the time, and there are new issues for us to go and solve. That one required the operator of the cloud to debug. And just to finish with a related example of why we like the operating system style virtualization, that bug that we worked on was pretty hard, and that was in the zones style virtualization. Consider what would happen for hardware virtualization. You have the kernel is scheduling onto CPUs, and then you have the guest kernel scheduling onto guest CPUs, which are mapped to the actual CPUs. Working on scheduler issues here become a nightmare. And this is one of the reasons why we don't like, we try not to do hardware virtualization. We prefer you use OS virtualization. It's easy to debug. And I had a particular network performance issue on hardware virtualization that took weeks and weeks and weeks to debug. And Robert Mustaki was helping. And there's the wall of the Joyent office where we had all the printouts of DTrace output and flame graphs to try and figure it out. It's extreme, the most difficult problem I've worked on for years. And it was because it's the tricky dance between the guest kernel schedulers and the host kernel scheduler. But DTrace made it possible. It even used a bit of system tap in this to solve that one. So thank you. That's a quick rundown, DTracing the Cloud, and the sort of things we're doing. Any quick questions before we move on to the next guy? Yes, Dan?
You're enabling some probes in zones. The TCP IP stacks you instantiate in the zone have their stack ID. Can you get some of the network probes to be zone happy? Is it theoretically possible, or is there more kernel separation stuff I'm missing?
So Dan said, is it theoretically possible? Because we've recently put more providers inside the zone. We haven't done, say, TCP provider yet. I think in theory it may be possible because the TCP connections, you're right, they do know which zone they're responsible for. We just need to do that engineering work, and that will enable the users of the cloud. It will enable more things. Possible but difficult.